similar detail, the group of isometries of a perfect polygon with n vertices. So the considerations are exactly the same as in the case of the square. Just instead of 4 vertices, we're dealing with n vertices. So we will position our ideal polygon just in the same way as we positioned the square, with one of the vertices on the x-axis. And then, since all the angles are the same, it will be preserved by a rotation by which angle? So now that we're dealing with n vertex perfect polygon, we know that it will be preserved by a rotation around the origin by 360 over n. That will be one of the symmetries of the perfect polygon, which we will denote rho. And what would be another symmetry? Well, obviously reflection around the horizontal axis. So against the horizontal axis, just as before, we will call it sigma. So this will be the two basic isometries which will build or generate the whole group. So in a moment we will see that just like with D4, the whole group will be generated by these two isometries. So these two isometries preserve the polygon. Hence, their various combinations, their various compositions also must preserve the polygon. So that means that we have various rows all the way through row to the n. If we have n vertex perfect polygon, which will be identity. And again, let's multiply on the right by sigmas. In addition, we will have all elements of this form: rho sigma squared, rho squared sigma, all the way through rho n sigma, which is just sigma. And this will be all rotations of even isometries, and this will be all odd isometries. So we don't know that there is actually nothing else. We don't know yet that these are all the isometries in the group. But how many of them there are? There are 2n distinct isometries. Again, why distinct? The top ones and the bottom ones can't mix because they're even and odd, while it's clear that the top ones are all distinct, and the cancellation laws will also tell us that the ones on the bottom are all distinct. So we have 2n distinct isometries. In the group, and from the considerations, combinatorial considerations, how many possibilities for a symmetry of a perfect n go on? Well, one vertex can go to n possible vertices, and then the second one have to go to one of the adjacent ones, so 2 choices. N choices for the first times 2 for the second, so 2n possibilities, so we have at most 2n distinct isometries. We have at least and at most, so that means there are 2n distinct isometries exactly in the group. So the symmetry group for the perfect polygon has the order 2n. And then we must say that it is generated by rho and sigma and nothing else. So it has 2 generators. We denote the group of symmetries of n vertex perfect polygon by Dn, and this is called the nth dihedral group. And we can also calculate the Cayley table, all possible multiplications of all possible elements, using the fact that sigma times rho to any k will change places as what? So first of all, again, we have the even transformation, more precisely rotation around the origin followed by reflection on the origin means it's another reflection in a line through the origin, means it's an involutive transformation, so we have this is equal to its own inverse. In other words, it's equal to rho minus k sigma. Just add n and we have rho n minus k times sigma. So we know how to change, how to commute sigma through rho to the k. We'll get sigma on the right and the rho n minus k on the left. And of course the same result you could have obtained using the conjugation theorem about conjugating rotation with reflections. So from that theorem, rho in the middle conjugated with sigma, a reflection against the x-axis, must be what? It must be the rotation, of course about the same center, about the origin, but by which angle? What do you think? Well, since sigma is an odd isometry, it will be the opposite angle. It will be minus angle corresponding to this rotation, or in other words, we have here rho minus k, which is the same as rho n minus k. So that amounts to exact same identity. So we know how to fill in Cayley table for the nth dihedral group. So we know everything about nth dihedral group. Indeed, the first n rows for dn are easy to fill along the same way as we filled the first n rows, row to row n, the first 4 rows for the d4 for the group of symmetries of perfect square. So rho n, which is identity sigma, rho sigma, and so forth until rho. Oh, well, we should start with identity actually. So we only go to rho n minus 1. Here we also go to rho n minus 1 times sigma. So the first n rows will be easy to fill, starting with identity rho n minus 1. But then we'll have to fill the crucial row when we multiply sigma on the left with everything else. So that is filled using this identity. And after that, the rest is again easy. So we have the Cayley table.